My name is Pragya Srivastava. I am a student of BSc Semester 6 Regular. My college roll number is 225070 and my topic for presentation today is field. Now, any algebraic structure f, plus, dot is called a field if it's a commutative ring with unity having multiplicative inverse of every non-zero element of it. For example, q, plus, dot or r, plus, dot or c, plus, dot. These are examples of field. All of these are field. Now subfield. Any non-empty subset S of a field F is called a subfield of it if S, plus, dot is also a field. For example, set of real numbers R is subfield of C plus dot. Now a theorem. The necessary and sufficient conditions for a non-empty subset S of a field F to be its subfield are: first is, for all a, b belongs to S, this gives a minus b belongs to S. Second point is, for all a, b belongs to S, this implies that a into b inverse belongs to S. Proof for necessary condition, that is this: if S is a subfield of field F, then S, plus, dot is also a field, so its subgroup of F under addition and multiplication. Hence, condition first and second are quite obvious. These are necessary conditions. Now sufficient condition. If 1 and 2 are given and we have to prove S is subfield of 1, if A belongs to S, A belongs to S, this implies that A minus B belongs to S. This implies that 0 belongs to S. This again implies additive identity exists in S. If 0 belongs to S, A belongs to S, this gives that 0 minus A is equal to minus A belongs to S. This gives that additive inverse of element of S exists. Also, for A belongs to S and B belongs to S, gives A belongs to S and minus B belongs to S, gives that A minus brackets में minus B is equals to A plus B belongs to S. This shows that S is closed under addition. As associativity and commutativity are always obvious, so S, plus is an abelian group. Now this is an abelian group. From 2, that is second one, A belongs to S, A belongs to S gives that A into A inverse is equal to 1 belongs to S. Hence unit element exists in S. Also, for 0 not equal to A belongs to S, 1 belongs to S gives 1 dot A inverse is equal to A inverse belong to S. Hence, multiplicative inverse of any non-zero element exists in S. Again, if A belongs to S and B belongs to S gives A belongs to S, B inverse belongs to S. This implies that A brackets में B inverse का inverse is equal to AB belongs to S. This is A into B inverse का inverse. Okay. Now, so S is closed under multiplication. Also, associativity and commutativity are always obvious. So, S, dot is also an abelian group. Now, this is also an abelian group. This was an abelian group. Now, this is also an abelian group. Distribution laws will hold in S. It is in F, so s comma plus comma dot is a field. This gives that S is a subfield of field F. This characteristic of a field. For any field F, the least positive integer n, for which n is equal to 0, where e is multiplicative identity of field, is called characteristic of field. Theorem related to this is the characteristic of a field is either 0 or a prime integer. So proof for this is by definition, if n is the characteristic of field F, then ne is equal to 0, where e is unit element of F. If order of e is infinite, then ne is equal to 0. This implies that n is equal to 0. So the characteristic becomes 0. But if order of e is finite, n is not equal to 0. Now to show that n must be prime, let if possible n is equal to n is equal to n1, n2. Now n1 is not equal to n and n1 is not equal to 1 and n2 is not equal to 1. By ne is equal to 0, we show that n1 dot n2 e is equal to 0. This implies that n1e, n2e is equal to 0, n1e is equal to 0 and n2e is equal to 0. It is impossible for n is least positive integer such that ne is equal to 0 gives that n is prime. Now, modular field. Fields with non-zero characteristic are known as modular fields. Note, characteristic of a field is equal to characteristic of its subfield. This is very important, that characteristic of a field is always equal to characteristics of its subfield. Let's discuss few other parts, that are field extension. Let F be a subfield K, then field K is called an extension of field F. For example, first is as q comma plus comma dot is subfield of r comma plus comma dot, so r comma plus comma dot is an extension of q comma plus comma dot. Second, similarly, c comma plus comma dot is an extension of r comma plus comma dot. Third is q under root 3 is equal to a plus b under root 3, where a, b belongs to q. It's field extension of q comma plus comma dot. Now degree of field extension. We know that any field forms a vector space over its subfield. Hence, Kf will be a vector space if K is field extension of F. Dimension of vector space Kf is called degree of K over F. It is denoted by K is to F. Extension. If degree of a field extension is finite, then it is called finite extension. Otherwise, it will be an infinite extension. That is, for extension K of field F, if this is equal to finite, then it will be a finite extension. But if this is equal to infinite, then it will be an infinite extension. The example regarding this is given here. So my topic ends here. Thank you so much.